Alright guys, today what we're going to be going over is how to how to do the problems on the test, especially on the review. So we're going to start with finding patterns of sequences, okay? So what you notice in here is you've got -5, 25, -125, 625. When it comes to numbers, it's pretty easy to figure out what the pattern is, because most of the time you're going to be seeing you're either going to be multiplying, dividing, adding, subtracting to pretty much get to the next number. So when we look at this, -5 to 25. Well, I could be adding 20. Okay, if I was adding 20, or actually in this case it would be 30. That would mean that I would be adding 30 each time. But if you notice, from here to here, it's 30. From here to here is not 30. Alright? So obviously adding can't be it. Subtracting really can't be it. So it's either got to be multiplying or dividing. Well, I know that from getting from 5 to 25, I had to multiply by 5. But notice how it's -5 and +25. So the only way to get from a negative to a positive is to multiply by negative. So we had to multiply not only by 5, but -5. So this went times -5. Alright, to here. This times -5 got to here. This times -5 got to here. So that would be our pattern. We would just put down multiply by -5. That's all you gotta do. That's all you gotta tell me is that's the pattern. You're multiplying by -5 each time. The next one, we're going from 5, 1, -3, -7. Really, you can probably tell by now that it's going down. Alright, it's going down. So most likely we're going to be subtracting by something. So we figure from 5 to 1 is -4. From that to that, -4. And from that to that is -4. So all you'd have to write down is subtraction by 4. Okay, something like that. Something to let me know that you are on track, you know what you're doing. The next part is really the idea of doing sequences or figuring out the number in a certain sequence. Well, the easiest way, alright, the ones that are going to be on your test are going to be using letters, alright? The easiest way to look at this is we got to figure out first how many terms are in each pattern. So we have O, M, G, B. Alright, that's one set. And then it starts over again at O, M, G, B. So every time it's going O, M, G, B. So there's only 4 different numbers in the set. So when there's 4 numbers in the set, this is how we end up doing it. So we know we want the 54th term. So what we're going to have to do is called long division. So long division. What you do is you start by putting the number you're dividing, alright, on the inside, and put the number you're dividing by on the outside. So we're dividing 54 by 4. So first thing is to see is, can 4 go into this first number on the inside? Can 4 go into 5? Yes, it can go in one time. So what we do is take 1 times 4 and we put 4 down here. Since 1 times 4 is 4, we subtract 4 away from this object. We get 1. Now, 4 can't go into this 1, so we have to bring down the second number we have, 14. Alright, it becomes 14. How many times can 4 go into 14? Well, 3 times. 3 times 4 is 12, so we subtract 12 and we get 2. What this is known as is the remainder. Okay? We have a remainder of 2. We have a number that can't technically be divided by 4. So 4 can go into 54 13 times and have a remainder of 2. So what we look back is we look at the actual sequence. It goes from O, M, G, B. Well, the remainder is 2. It has to be the second thing in the sequence, which would be M. So the second term in my sequence is M. Okay? Now, another way to think of the remainder, alright, is if you're using a calculator and you've forgotten how to do long division, alright, is to actually use your calculator. Okay, so if we took 54 divided by 4, we would get 13.5. All right, we're looking at we want to look at the front number. Anything that's not behind a decimal mark, we want to look at. So 13, all right, just like the 13 over here, this one, we're just going to take it and multiply it by 4. 4 times 13, we get to 52, okay? This is why it's faster and easier. If you use your calculator, this is how you would do it. You would end up getting 13 times 4, which equals 52, all right? That's not the 54 that we originally wanted. So what we had to do now is look at it as, how many numbers do I need to get to 54? That is what a remainder is okay? The extra stuff that needs to be added on at the end. So the remainder is 2. So we'd have to get, if we added 2 to 52, we'd end up getting 54. Okay? So once again, to figure this out by using a calculator, you first take the number, you divide it by the number you're dividing by. Alright, you get this number. You look at the front number, okay, the number in front of the decimal. Alright, and you're going to take that and multiply it by the divisor, or the thing that we were dividing by to begin with. So we take 4 times 13, we get to 52. And then we take 52 and we add up how many numbers we need to get to the number we originally started with, which was 54, and we needed 2. So once again, your remainder is 2. So, okay. Next part. Same thing with this part, okay? So, we notice that Monk is M-O-N-K, M-O-N-K. So you have 1, 2, 3, 4 parts in this sequence. Okay, it starts over after the 4th letter. We're trying to find the 17th term. So what you can do is, one, you can write this out until you have the 17th term, or you can just do a simple long division problem. So since there's 4 terms, we have 4 on the outside. We're trying to find the 17th term. We put the 17th term on the inside. 4 doesn't go into 1, so we can't write anything there. So next part is, can 4 go into 17? Alright, the first 2 numbers, yes, 4 times. 4 times 4 is 16. If we subtract 16, we'll end up getting 1. That's a remainder of 1, meaning the first number in our sequence, which is 1. If you were doing a calculator, you'd have to do 17 divided by 4. You'd get 4.25. Remember, we're looking at the first number in front of the decimal. That would be 4. We're not going to worry about the 0.25. So we take the 4 times the divisor, 4 times 4. So 4 times 4 equals 16. How many numbers would I have to add to 16 to get to the original number? Alright, which is 17. And that'd be 1. So my remainder would have to be 1. If we look back at the sequence, what's the first term in the sequence? That would be M again. Now, conjectures. What conjectures mean is making a rule, a guess of some sort that you think's going on in the area. For the first one, the product of 2 odd integers. We can't really make a conclusion or a conjecture until we've actually tried out some of the problems. So I showed you here, 3 times 7 equals 21. 9 times 5 equals 45. Any 2 odd numbers. You could do 21 times 13. Now if we did 21 times 13, we'd end up getting, sorry guys, can't do this in my head, I gotta do this on a calculator. We end up getting 273, okay? So 21, 45, 273, we gotta look at all these answers and figure out what is something they all have in common. Well, honestly, it doesn't look like they have much in common, except for the fact that they're all odd numbers, okay? They're all odd numbers. So what we can say the conjecture of this is that when you multiply 2 odd integers, that means numbers that don't have decimals and can't be divisible by 2, alright, would be that it makes an odd integer. Okay, it makes an odd integer. Then we're looking at the sum of an odd and an even number. The sum of an odd and even number. So odd meaning, okay, the numbers that aren't divisible by 2. Even are numbers that are divisible by 2. And integer means no decimals. So we've got something like, we'll say 4. 4 is our even number. Alright, this is the even. Plus the odd number, let's say it's 7. Alright, that gives me 11. This is odd. Okay. Even. Let's go with 2 plus, I don't know, 11. Which are odd number. So even odd equals 13, which is once again an odd number. So you'll notice that whenever you add an even and an odd together, you get an odd. Even, odd together, you get an odd. So when you the sum, meaning addition, of an odd and an even integer is an odd integer. Alright? Is an odd integer. Whoop, didn't mean to not write that on there. So, even odd makes odd, even odd makes odd. The conjecture we can make is the sum of an odd and even integer is an odd integer. Okay? Counterexamples. Alright, remember, counterexamples, to counter something means to, really, counterexample means to give proof that something is false. That's what we're trying to do, is give proof that something is false. When you know something is false, to say that, like, give a reasoning why it's false, or an example of why it's false, called a counterexample. Now, here, we're going to try to think of something that gives us a counterexample. All four-sided figures are rectangles. So, what it's trying to say is all four-sided figures are rectangles. If we can think of one figure, it doesn't matter what figure it is, one figure that has four sides that's not a rectangle, then we've proven this statement false, and we've given a good counterexample. So, rectangle, let's say, you could have said square. Rhombus, alright? Rhombus, parallelogram. Sorry. I don't know how to spell parallelograms. We're just going to skip that one. Parallelogram. Then you could have said trapezoid. Alright. Any of these would have worked. These are all four-sided figures that aren't rectangles. So what we can say is that our counterexample is one of these. Circle are the only shapes with no sides. Okay, really shape, I'm not saying it's a polygon, anything like that. I mean, technically, I could just have drawn this. This has no sides, and it's obviously not a circle. Alright, this is a shape, however. I mean, shapes are pretty easy. They don't really have a definition of what a shape is, so I just made a squiggly thing. But if you wanted to be more exact, you could have said something like an oval. Alright? Oval, alright, it's not a circular shape, but it still has no sides. So really all a counterexample is just proving something's false. Why is something false? Well, let me give you an example why it's false. That's the easiest way to discount something in life, alright? Now, the next part is, we've been practicing a lot. I understand we've been practicing a lot, but we still need a little bit more practice on it. Conditional statements and their negations. So, let's look at the first part. Kangaroos are marsupials. So, if you don't know what a marsupial is, it is something that carries its baby in a pouch. These are things like kangaroos, koalas, wombats, a lot of other things that live in Australia. So it pretty much is its own breed of mammals, and it's just something where there's no embryonic sac, the mammal doesn't have embryonic sac, so it has to crawl into a pouch. Okay. So kangaroos are marsupials. We have to make an if-then statement. So we have to make an if, something, then. Okay. So first it's looking at kangaroos. So we can say something like if it is a kangaroo. Kangaroo. Okay, if it is kangaroo. Okay, what about it being a kangaroo? Alright, well, we're going back to our statements. If it's a kangaroo, then what? Then it is a marsupial. Okay? If it is kangaroo, then it is a marsupial. That's what we're trying to say. A hypothesis. Remember, the hypothesis is anything that follows the if statement. So what follows our if statement here? It is a kangaroo. That'd be our hypothesis. It is a kangaroo. Okay, it is kangaroo. What's the conclusion? Well, the conclusion is anything that follows the then statement. So, it is a marsupial. So, hypothesis is it is kangaroo. Conclusion, it is a marsupial. So, the negations, meaning, alright, we have three different negations. We call it converse, inverse, and contrapositive. Those are the three negations we're looking at. First, the converse. Okay, remember guys, converse, okay? What the converse does is it switches the hypothesis and the conclusion to make a new if-then statement. Instead of saying if it is kangaroo, we're going to say if it is a marsupial. Alright? If it is a marsupial. Okay? Now, since we made the conclusion our hypothesis, now we have to make our hypothesis our conclusion. Then it is a kangaroo. Okay? So, if it is a marsupial, then it is kangaroo. Truth statement, truth value. Truth value just means, is it true or false? Now, if it's true, then it's true. It's always going to be true. Doesn't matter if it, we don't need anything else beyond that. But if it's false, we have to provide a counterexample. Remember, the counterexample is just something that proves that it's false. Well, in this case, if it is a marsupial, then it's a kangaroo. Well, let's look at that. Let's analyze this. If it is a marsupial, well, if it is a marsupial, then what? It is a kangaroo. Well, there's more than just one marsupial. So we would say this is false. Our counterexample would be something like a koala. Alright? Koala is a marsupial, but it's not a kangaroo. So obviously this idea has to be false, because not all marsupials are kangaroos. Okay. Inverse. This is where a lot of people get confused. They automatically see converse, and then they try to do the negative version of that. Now, inverse, alright? Inverse goes with the conditional statement. It goes with the conditional statement. You have to essentially use the negative words of the conditional statement. So, the conditional statement is if it's kangaroo, then it's a marsupial. What we'll say is if it is not a kangaroo, then it is not a marsupial. If it is not a kangaroo, then it is not a marsupial. So notice once again that the inverse, alright, goes along with the converse. These two, alright, this is positive words, negative words, positive words, negative words. Now, the converse, okay, actually, I'm sorry, let's go with the truth value before we do that. Truth value. If it is not a kangaroo, then it is not a marsupial. Once again, you're saying that if the animal isn't a kangaroo, then there's no possible way it could be a marsupial. Well, once again, that's false. We know that's false because we just provided an example. Just saying the same example again to prove why it's false is okay. Koala, once again, it proves that a koala is not a kangaroo, but it's still a marsupial. What we're trying to do, alright, is see if the hypothesis is true, then the conclusion is also true. Alright? Both of these parts have to be true for it to be true. If it's not a kangaroo, okay, so assuming that's true, then it's not a marsupial. Well, this is not a true statement. Alright? This whole thing's not a true statement. So finally is our contrapositive. This is connected to the converse. Contrapositive, converse. So, like we did with the inverse in the conditional statement, we're going to use negative words. If it is not a marsupial, then it is not a kangaroo. Alright, if it is not a marsupial, then it is not a kangaroo. Now, let's see if that makes sense. If it's not a marsupial, okay, so it's something that doesn't have its babies in a pouch. Okay, so something besides that, then it's not a kangaroo. Well, that's true. I mean, if it's not a marsupial, there's no possible way it could be a kangaroo because kangaroos are marsupials. So, this statement is true. We don't say anything else besides that, we just say it's true. Alright? Let's go on to the next one. I live in St. Louis, Missouri. Okay? Now, really trying to figure out the conditional statement is sometimes hard when you're looking at this stuff. So let's look at it. I live in St. Louis, Missouri. Well, if I what, then I what? Well, if I live in St. Louis, then what? Then I have to live in Missouri. So that's what our conditional statement is going to be. If I live in Missouri, in St. Louis, then I live in Missouri. Alright, if I live in St. Louis, then I live in Missouri. Hypothesis, once again, thing that follows the if statement. I live in St. Louis. Conclusion, anything that follows the then statement. I live in Missouri. Alright. Converse. Once again, converse switches the hypothesis and conclusion. If I live in Missouri, sorry guys, I'm writing a little bit sloppy. If I live in Missouri, then I live in St. Louis. Now, once again, we have to figure out, is this true or false? If I live in Missouri, do I automatically live in St. Louis? Well, that's not true. I'm currently making this video from St. Charles. I obviously am not in St. Louis. So, but I'm still in Missouri. So that means that even though I live in Missouri, and I don't live in St. Louis. So this part's true, but this part's not also true. So the whole thing has to be true for it to work. Alright? So this is false. Alright? For example, St. Charles. Or St. Peter's works. Either way works. I mean, you could be in either one, still not be in St. Louis. Inverse. Well, inverse once again. Inverse, remember, is connected to the conditional statement. Inverse conditional statement. So, if I don't live in St. Louis, then I don't live in Missouri. If I don't live in Missouri, if I don't live in St. Louis, then I don't live in Missouri. Once again, it's saying you don't live in St. Louis. Well, could I live somewhere else besides St. Louis and still live in Missouri? Well, yeah. If I don't live in Missouri, if I don't live in St. Louis, I could live in Kansas City and still live in Missouri. So the statement's false for the fact that you can not live in St. Louis but still be in Missouri. So, false. Let's go with Casey. Alright, just because of the Royals. What is contrapositive? Alright. Once again, the contrapositive is connected to the converse. And remember, using negative words with the converse. So if I live in Missouri, then I live in St. Louis. Let's use negative words. if I live in, if I, sorry, don't live in Missouri, then I don't live in St. Louis. Now, I know most of you guys are going to tell me that this is technically incorrect too, which technically it is because of East St. Louis, but we're going to pretend that that part's not really part of St. Louis, just for the sake of this argument. I do apologize for making that exception. Normally I wouldn't, but when I created this, normally what should happen is that unless the thing is a biconditional statement, all right, which we'll get to here in a little bit, should always go, the conditional statement should always be true, the converse should always be false, the inverse should always be false, and the contrapositive should always be true. That's how these logic statements work. All right. In this case, technically the conditional statement wasn't entirely true to begin with, but using the fact that we're saying that all people who live in St. Louis live in Missouri, we're going to continue with that thought process. So, if I don't live in Missouri, then I don't live in St. Louis. By the definition of saying, St. Louis, not East St. Louis, then yes, that's true. We're going to say that's true, okay? We apologize in advance. Alright, next part. Horror movies are scary. Alright, so Halloween coming around, I had to put that in there. Sorry, guys. If then statement, if, always starting with the in order. Alright, we always want to go horror movies scary. Notice how we went St. Louis, Missouri. We went kangaroos, then marsupials. Alright. If it is a horror movie, alright, if it is a horror movie, then it is scary, alright? Which is not always true, but we'll pretend that those who make horror films are actually doing the job that they're supposed to be doing. Hypothesis, anything that follows an if. It is a horror movie. Alright. Just to let you know, nothing's going to be ambiguous or left of thought on the test. So you're not gonna be wondering, is this or is this not true? You're gonna be like, yeah, that's true or not true type of thing. Hypothesis: it is a horror movie. Conclusion: it is scary. Alright, it is scary. Converse. What is our converse? Well, once again, we flip the hypothesis to conclusion, so now it is, if it is scary, then it is a horror movie. Now, once again, that's not true. I could be attacked by a bear. That'd be pretty scary. I could be crashing in a plane. That'd be pretty scary. It's pretty much anything that's a scary event really makes this false. Alright. False. Let's go with plane crash. Alright. Plane crash is pretty universal. If you're going down on a plane, no one's going to be like, yay, I'm going down on a plane. Okay, inverse. Inverse, once again, is connected to the conditional statement type of thing where it's always negative words. If it is not a horror movie, then it is not scary. Once again, that is actually false because, I don't know, let's go with bear attack. Alright, bear attack's pretty scary, right? Alright. Bear attack's not a horror movie, or at least I've never heard of it before. Bear attack's not a horror movie, but it is probably scary. Alright, so that's what we're trying to look for. Something that was, it's not a horror movie, but is scary. So something that proves this true, but this part false. That type of thing. Okay? Counterexample, or I'm not going to contrapositive. Contrapositive, remember, goes with converse. So, if it is not scary, then it is not a horror movie. Alright, once again, we have the assumption, we have the assumption that all horror movies are scary, so under that assumption, we're going to say if it's not scary, then it's not a horror movie. Well, obviously, if it's not scary, and we have the assumption that all horror movies are scary, then it can't be a horror movie. So we're going to put true. That's going to be true. Okay? Remember, usually the conditional is true. The conditional is true. The converse and inverse will be false unless it is a biconditional statement. And the contrapositive should always be true if the conditional statement is true. Do apologize about the time and how long it takes really to go through this stuff, but really this is what needs to be helped with if you need it. Alright, good definition. A good definition is, it's a good definition if it can be written as a biconditional statement. Remember, the biconditional is the if and only if statements, okay? So, cats are animals with fur. Well, what's cool about biconditional statements, alright, is it's something that's true forwards and backwards. That means that if we were to write this as a a conditional statement and a converse, that both would be true. So before I even write the biconditional statement, let's just see if we make a conditional statement and its converse, if they're both true. Let's say if it is a cat, then it has fur. Alright. Let's just pretend that the hairless cats don't exist because they're not real cats. We'll just pretend they're not real cats. If it is a cat, then it has fur. True. We'll say that's true. Alright, that's a conditional statement. Converse. Remember, you cannot make a biconditional without both of these being true. Converse is if it has fur, then it is a cat. That is actually false. Alright, you got dogs, you got bunnies, you got anything that really has fur, and there's a lot of things that don't have that fur that aren't a cat. So that's false. So technically we can't even write this as a good definition. So this is actually be a bad definition. Alright. This is a bad definition because we can't write a biconditional statement. Alright, if you can write a biconditional statement for it and it's true, then it's a good definition. If you can't, it's false. Okay. Dolphins are mammals that live in the ocean. Conditional statement. If it is actually right, no biconditional in here. Just for help. Alright. If it is a dolphin, then it is a mammal that lives in the ocean. Alright, that's true. Alright. Dolphins live in the ocean. Converse. Alright. If it is a mammal that lives in the ocean. Oop, I'm sorry, I've been writing all this off page. Ocean. Then it is a dolphin. That's false. Alright, so true, false. Since that's false, it's a bad definition. Now biconditional. Bad definition. Alright. Triangles only have 3 sides. Conditional statement, if it is a triangle, then it only has 3 sides. Alright, so if it's a triangle, then it only has 3 sides. That's true. Alright, converse. If it has only 3 sides, and then it is a triangle. That is true. So the biconditional hand cramp. Sorry. I'll let you just soak that in for a second here. Okay. If it is a biconditional, it's okay. So essentially, biconditional once again is you're dropping the if and then from the conditional statement and just write if and only if between the hypothesis and the conclusion. So between the hypothesis and the conclusion, we write if and only if. It is a triangle if and only if and only if it has 3 sides. Good definition. Okay. Water is made up of only 2 hydrogen and 1 oxygen atom. Alright, so writing that down would be if additional statement. If it is water, then it is made up of H. I'm just going to put H2O. Okay. That way it's a little bit easier to write. Converse. If it is H2O, it is made up of H2O, then it is water. So once again, both of those are true, so biconditional. Alright, biconditional is remember, you're taking the if then out of the conditional statement and you're writing if and only if between the hypothesis and conclusion. It is water if and only if it is made up of H2O. Alright, that's a biconditional. So, considering these two, okay, try the triangle one and the water one, they both have a biconditional statement that's true. They're both good definitions. Alright? They're both good definitions. Dolphins and cats, okay, I explained why. Both of their converses were wrong. There's whales that are mammals that live in the ocean, so that's why it can't be this one's not a good definition about dolphins are mammals that live in the ocean. Alright. and cats are animals with fur. That's not a good definition because there's more than one animal with fur. Okay. Next thing. I do apologize why this video is so long, but it has to be. Alright, so fast forward to anything you need to skip over. Alright, so find conditional and converse from the following biconditional statements. Alright, so when you're looking at this thing up here, we are actually looking at really trying to make a conditional statement out of this biconditional statement. So essentially this part right here, the if and only if part, can be kicked out. Alright, what we're going to really worry about is this, which is the hypothesis, and this back part, which is the conclusion. Alright, we can just kind of just mark that out. So remember, the conditional is the if, hypothesis, then conclusion. So if it is a monkey, then it is a primate with a tail. Alright. Converse. Alright, remember you flip the hypothesis and conclusion. If it is a primate with a tail, then it is a monkey. Alright. So once again, all you're trying to do is write your conditional and converse from this stuff. Once again, we're going to look at the if and only if. We're going to cross it out because we don't need it. That's part of the biconditional. And we're looking at the hypothesis and the conclusion. Alright, hypothesis and conclusion. So, to angle the supplementary, if and only if their sum is 180. So it'd be if then is the if two angles are supplementary, then their sum is 180. Alright. Converse. Okay, same thing. But flipped. So if their sum is 180, then they are supplementary. Alright. Now, most of the time we really care about the grammatical stuff. But right now you guys are learning. You're going to make grammar errors just like I did, considering the fact that I don't have a subject. I just have pronouns. So, you know my statement. I understand what you're trying to say. So if you don't really use a, let's say, grammatically correct statement, I'm not going to count off for it. It is square if and only if. It is four equal sides and one 90-degree side. So again, honestly, I don't really have to do this over again because I think you guys get it by now. Hypothesis, conclusion. Alright. So you're going to do the same thing with the conditional and converse as the last two. Alright, using the law of detachment to make a conclusion. So, law of detachment. Okay, so law of detachment is, once again, is you have an if-then statement. If-then statement. Now, you're looking at this little thing right here, which is the statement after the if-then statement. So, if it is within 3 miles of your house, then it is within walking distance. So, we have two parts, a hypothesis and conclusion. So, McDonald's, alright, it agrees with your hypothesis. So, agrees with the hypothesis, so your conclusion is it is within walking distance. Alright. So, If it agrees with your hypothesis, then your conclusion is this, is whatever the actual conclusion is. Now the next one, if you can twerk, then you will go to the club. Eric Goat went to the club. Now this does not agree with our hypothesis. Doesn't agree with hypothesis. Alright? Doesn't agree with hypothesis, so no conclusion. No conclusion can be made. The Avion makes a lot of money. So the thing is, if you make a lot of money, then you can make it rain. The Avion makes a lot of money, so this agrees. So the conclusion is you can make it rain. Alright? It's the whole idea behind that. Alright, so that is law of detachment. Law of syllogism, alright? Law of syllogism states. Alright, what we're looking at is you're looking to see if you have okay, so if you do laundry, then you will have clean clothes. If you have clean clothes, then you will be fresh, complete. You're looking at that the if and the then, alright, the if and the then, alright, that you have an if, meaning a hypothesis statement, and a then, meaning a conclusion statement that say the same thing. If you do, what we can do is we can cross them out. Cross out the things that got alike. So what we're left with is, if you do your laundry, then you'll be fresh as can be. And this is what the law of syllogism tells us we can actually do, is that we can essentially cross out the middleman and just make the conclusion of the original hypothesis and the end conclusion. So, if you do your laundry, then you will be fresh as can be. Alright. If you buy a hat, then you will take the sticker off. If you take the sticker off, then you will not look weird. Also, once again, your if. Alright, you have a then statement and if statement that say essentially the same thing. Cross them out. If you buy a hat, then you will not look weird. Alright, here's the tricky one. If you watch the NBA, then you'll have to have a favorite team. If you watch the NFL, then you will have to have a favorite team. Alright, so notice the things that repeat are two then statements, alright? They're two then statements. So we have no if, we have no hypothesis and conclusion that match. So since we don't have a hypothesis and conclusion that match, there is no conclusion to be made. Alright, so what you're going to notice between these, they have a then and an if, then and an if. This one just has two thens that say the same thing. So we can't really do anything of that, so we don't really care. Write your own law of syllogism statement and your conclusion that can be made from it. So you're just going to do like things up here, like the same thing up here, except for in your own thing. So like, I don't know, just write, I don't know, if you like the color green. Then you like I don't know, grass. If you like grass, then you should, I don't know, be a botanist. Alright. Alright, there's your if-then statements. Those both of them. then the conclusion would be, if you like the color green, then you should be a botanist. Something like that. Something as simple as that. That's all I'm looking for on this test, is for you to write something like that. Alright, the hardest part of this thing is really what's coming up next. The only real part that's going to be confusing is kind of these two parts. Like this down and this first one, I expect you guys all to get that, but these two would be the ones I expect you guys to get wrong. Alright, so given C is the midpoint of AB, so you know that C is the midpoint of AB. What we know about midpoints is that it cuts things in half and makes them into two congruent parts. So when it gives you the statement that originally was part of the given statement, we just write given. That's all we got to write, given. Because they gave it to us. They told us C was the midpoint. We didn't have to prove that. They gave it to us. So now, what you're really trying to do in each of these steps is show me what happened from step to step. So from here to here, what happened? Well, from here to here, what we stated is that AC is congruent to BC. Why do we know AC is congruent to BC? Well, it's part of kind of the definition of what a midpoint is. A midpoint cuts something in half. All right, essentially is a segment bisector of something, so it creates two congruent parts. So what we can say about this is that it's a definition of something. All right. It's a definition of what? Well, it's part of the definition of what we call a midpoint. A midpoint cuts something in half, makes it congruent. So it's part of the definition of a midpoint. All right. Now the next statement, from here to here. What's happening? Well, from here to here, we went from congruent to equal, and we don't have the lines above the AC and the BC. So what that means is that the AC and the BC, what we're trying to ask for is the measurement of. Alright, without the line above it, it's trying to say the measurement of these two things. So the measurement of AC is equal to the measurement of BC. Why do we know that? Well, we know that because of this last part. What does congruent mean? Congruent means that the measurements are equal. So it means that they're the same length. We just say congruent because they're two different objects. So when we say the measurement is equal, well, that's the definition of the congruency. Alright? That's exactly what it is. It's the definition of congruency. Congruency, so from here to here, it tells us that these are congruent. And because we know these are congruent, their measurements have to be equal. Definition of congruency. Now, the next couple of parts, it's pretty easy. You're just using those little definitions that we had on 3 point, or I think it's 2.5, 3.5. Can't remember what they put on there. The proofs one. So from here to here, we replace with the actual lengths, x, 7x minus 9, and 4x plus 6. We replace it with AC and BC. So when you replace something, no matter what it is, if it's me being replaced by a teacher, you being replaced by a fellow player for your position, we always call that a substitution. Alright, so that's all you got to write is substitution. Okay. From here to here, after the substitution, well, let's see what happened. Well, the negative 9 went away. The only way to get rid of it, the negative 9, alright, is to add it to both sides. So we put addition. From here to here, what happened? Well, the 4x disappeared. Well, how did the 4x disappear? We had to subtract it away. The only way to do it, so subtraction. Alright, we usually call these properties. Properties. Okay. Finally, the 3 went away. So how did that 3 go away? Well, it's division property. And that's how that really works. Is you're always writing on the line below it what happened. So what happened from here to here? What happened from here to here? What happened? All right. What happened? What happened? That's what you write in these spaces for reasoning. Next part is right triangle. Pretty much it's a right triangle. What it's trying to say is that these two smaller triangles add up, are complementary. So they add up to be 90 degrees. Okay, that's what complementary means, is they're 90 degrees because it's given by this little 90-degree mark. All right, so given that, we got to prove that x equals 11. Once again, the first statement always given. So what's happened from here to here? Well, what's telling you is that two smaller angles, this angle and this angle, equal 90. Why do we know that it's 90? Well, what does this say? Complementary. Complementary means what? Two angles that add up to be 90. Well, when these two angles add up to be 90, that's the definition of what complementary is. Alright? That's part of the definition. We know that complementary means they add up to 90. Really, you're just looking, like, a lot of the times, if you don't really understand what's going on for the most part, it's probably the definition of something. So really trying to figure out what is the definition of, well, look at the previous statement. What did the previous statement tell you? Well, the previous statement told me that they're complementary, so it's probably the definition of complementary. Alright? Just in proofs, we really got to go like this step-by-step basis. Otherwise, the proof won't make sense. So that's why we're doing this like kind of obvious stuff. It's kind of obvious that two things are going to be 90 if they're complementary, but we still have to make the statement. Next part. Angles are changed with what their actual measurements are. Well, when you change something out, it's called substitution. From here to here, okay, they're on the same side. A lot of you guys were trying to call what this next step is the same thing up here. This to here is not called combining like terms. You only combine like terms if they're on the same side. So from here to here, what happened is we call that combining like terms. Alright, that's combining like terms. Okay, it's because they're on the same side, so all the terms combined into this. From here to here, what happened was 2 went away, so we call that subtraction. Finally, the 8 went away, call that division. Alright. So I'm saying these steps right here are pretty simple. It's just this, usually the middle, like the second or third step is the one that's going to be the hardest. Alright. Last step, last thing. And then I'll shut up. You guys can take this test at some point. Hopefully this week. Alright. Alright, so remember, when two lines cross, they create vertical angles. Vertical angles are the angles that are across from each other. It does not mean they need to be up and down from each other. They just have to be across from. So we've got two lines, create these two vertical angles and these two vertical angles. What we know about vertical angles, guys, is that they're congruent. Now remember, congruent means they have the same measure. Since these are the measures of the angle, what we can do is we can set them equal to each other. This allows us to go 9x minus 12 equals 6x plus 6. Alright, from here it's just simple algebra 1 stuff. Add 12, 9x equals 6x plus 18. Subtract 6x, subtract 6x. 3x equals 18. Divide by 3, x equals 6. Alright? That's all that is. Alright, once again, these are one type of vertical angles, the second type are the up and down ones. Alright, so this is what we're going to do the same thing. 5x minus 8 equals 11x minus 32. Alright, so all we got to do, once again, solve it. So let's do this. 5x negative 8 equals 6x minus 32 plus 32 plus 32, 24 equals 6x divided by 6 x equals 4. Alright. Yeah. Last but not least, understanding what these are. Alright, right angles. Okay, right angles are given by boxes. When you have two angles that add up to give you a box, means that these have to add up to give you 90. So that's exactly what we do. We take 7x, alright, plus 3x. Since they're two smaller angles, and they should equal the larger angle, which is this angle right here. So we set it equal to 90, since that's what a box means, is 90. Combine like terms first. 7 and 3 make 10x. Negative 5 make negative 10. Equals 90. Plus 10. Plus 10. 10x equals 100. Divided by 10. Divided by 10. X equals 10. Alright, this one's a little bit tricky because they're trying to trick you. This is probably going to be the one that looks like on your test. So please make sure you understand the trick. Alright, yes, this is a straight line equals 180, but it already tells you that this little part right here, this angle right here equals 90 degrees. Well, what does that mean this angle right here has to equal? Well, it also has to equal 90 degrees because it is the second part of a angle. These two, this angle and this angle, should be 180. It means this angle and this angle should be 90. So what we can do once again is add these up, set it equal to 90. Combine like terms. 18x minus 18 equals 90. Plus 18 plus 18. 18x equals 108. Divide by 18. Divide by 18. I believe that is x equals 6. Sorry. Alright. This back sheet, I don't really find it. Hopefully no one has a problem with. If you do, please ask questions. In class, you have until Friday to really ask these questions. I will do my best to help you with them. If you want to come out to school for tutoring on Tuesday or Thursday, I would be happy, because that means that you're trying to learn your grades. Everything else, once again, if you have any questions, comments, concerns, just let me know. Thank you.